Hello guys, this is Mostafa Salari. Today I would like to talk about how we can implement a simple mixed integer programming, otherwise known as MIP problem, in Python using Gurobi solver. This is going to be a very simple problem, but I think it's going to be a good guideline that if you want to work on more complex problems. Okay, let's see what is the problem that we want to implement in Python. Let's focus on this toy example. In this toy example, we have a graphical network which is directed, and by directed I mean the links in the networks have direction. We also have 5 nodes in this network, 1, 2, 3, 4, 5, and also we have 8 directed links. As you can see, the number of links are also mentioned on top of the links. In this network we have something called path. A path is a possible route or a possible path between 2 nodes in a network. For instance, here I define path 1 includes 1, 2, 3, 4. And these numbers here are representing the links including in a path. For instance, path 1, this line means path 1 includes link 1, 2, 3, and 4, which means we start from this node, we go and we use link 1, link 2, link 3, link 4, and we end up in node 5. Another path, for instance, path 2 includes link 1, 7, and 4, which means link 1, then we get to link 7, then we get to link 4, which means this path connects node 1 to node 5. Let's do another example. Path 5 includes link 4, 5, 1, and 2. Now we get back to the network. We start from link 4, then we get to link 5, yeah. Then we get to link 1, and the last link is link 2. So we start from here and we end up here. Basically, this path connects node 4 to node 3. Okay, now let's get to the formulation that we have for this network. In this network, the objective function is minimization. So what we try to do is to minimize. And we have here a summation, we have xa. xa is a binary variable, and the subscript a here shows links here. So basically what we try to do, we try to minimize the number of links here. But we also have a constraint, and the constraint here is rho or theta. I can say it, rho ARI times XA greater than 1, and also we have a summation on all links. As I said before, this A, the subscript A, represents the links, and this capital A is the set of links. So here in the constraint, we have this row. This row is a binary parameter. It's not a variable. It's a binary parameter that could get 2 values. It could get either 0 or 1. If a link is included in a route, then the cell associated with that link in route is 1, otherwise it's 0. What do I mean? Okay, let's get back to the example. We have here path 1. Link 1 is included in path 1. So rho AR1 should be 1. For link 1 and path 1 should be 1. Another example, link 7 is included in path 2. So rho 7, instead of A if I use 7, and instead of Ri if I use R2, which represents path 2, should be equal to 1, because link 7 is included in path 2. Okay, with this definition, let's get to see what this constraint does. And based on this constraint, because we also have the summation on links, and it should be defined for each route or path, as you can see here, For each path, at least one link should be selected. And as I said before, the XA is a binary variable that could get the value of 0 or 1. It gets 1 if link A is selected, and it gets 0 if it is otherwise. So here, this constraint technically enforces the fact from each path, one link should be selected. And having this constraint, we want to minimize the number of links that should be selected. And here also, this last line shows that XA is a binary variable that could get either value 0 or 1. Okay, with this definition on the problem, let's get to see how we can implement this problem in Python using Gurobi. Okay, now we get to the Jupyter Notebook page. I already brought it up. Okay, let's see how it starts. The very first step that we got to do, we got to import the Gurobi library. To do so, it's very simple. So we can write down from Gurobi py import star. Okay. By implementing this line, what we do, we basically import Gurobi library, or Gurobi py, known as Gurobi py, to the Python, so we can use it for the rest of the problem. Okay, now we get to the set. So the next step we got to do is a set definition. Set definition. As it's obvious from its name, we gotta define sets. So if we go back to the problem, how many sets do we have? Okay, we have a set of links, that's obvious here. We have a set of path, right? And also we have some nodes here. So we have 3 sets, set of links, set of path, and set of links includes 8 members because we have 8 links. Set of path include 5 members because we have 5 paths. And also set of nodes include 5 nodes because we have 5 nodes. Okay, now we get to the set definition. So we have 3 sets and we gotta define them. So let's define the list of sets here. So the first set I want to define is the set of path. So I use the capital letter P equals to. In this tutorial, I assume you have a basic understanding of Python. And so I want to let you know that for set definition, I'm using a list notation in Python. And the way to do it, I use square brackets. And inside the brackets, I write I for I in range. The range function is a kind of function in Python that it includes the lower bound, but it doesn't include the upper bound. So because we have 5 paths here, so I'm writing the range from 1. So now you tell me from 5 to 5 or 6. I should go to 6 because this upper bound digit is not included in range function. So basically this range function is from 1 to 5, including 5, and it doesn't include the 6. And that's why I gotta put 6 here, because if I put 5 here, it goes up to 4. Okay. The next set is the set of links, which I use the capital letter L equals to. Again, the same approach, I for I in range 1, 2, 8 or 9. 9, right? Because we have 8 links. You may ask, oh, can I use the same I here in this list and I here? Yeah, you're totally separate and you're totally free to do so. And also I'm using the I'm defining the set of nodes. I may not use it in the problem, but it's better to define everything that you have. Then if you need them, you can use them. If you don't, you can just leave it there. For that reason, I'm defining the set of nodes as well. The number of nodes we had in the toy example was 5, so very similar to the way I define path. I'm just gonna copy and paste it here. Okay, so that's how we can define sets in this problem. Let's get to the next step that we got to do, and it's parameter definition. And that means like we got to define all the parameters in the problem. Okay, to know what parameters do we have, let's have another look at to the problem. In this problem, one of the parameters we have is definitely this row. So that's one of the parameters we got. Also, we have this parameter, which is the P1, P2, P3, P4, P5. And it basically, this parameter tells us what links are included in each path. Okay, so far 2 paths, and let me tell you, it's better to define all possible parameters in a problem. Then you may not use some of them in the actual formulation, but it's better to define all of the parameters. So if in any case you need to use them, you already have them and you already defined it. Okay, let's first define the path. So to define parameters in Python using Gurobi, we gotta use dictionaries. Okay, let's focus how I can define the parameter of path, and basically this one in the Python. So as I said, we use dictionary notation. So we define something called path, and I assign an empty dictionary to it. So then we get to the first value of the path, and I use the key value. I put 1, basically means path 1 includes links 1, 2, 3, 4. Yeah, 3. Oops, 3 and 4. Okay. This is how you define path 1. Basically, by using so, I assign the key 1 to the path. So if I use this key, which is 1, it returns this value to me, which is the list of links included in this path. Okay, let's get to the path 2. 1, 7, 4. Let's get to the path 3. Includes links 1. I forgot 1683. 1683. And also we have path 4, which was including links 3, 4, 5, 1. Okay, I can double check 3, 4, 5, 1. Okay, and also we have path 5, which includes links 4, 5, 1, and 2. Okay. The next things I gotta define is this parameter, which is row. To define this parameter, what I can do is I can use the other parameter, which is path. So this parameter, let's define it as, just for fun, I'm going to define it as a theta, which is totally okay. So again, I'm using another dictionary notation here. So this theta basically represents this row here. It's not a big deal. So here, I define a for loop for P in P. What I want to do, I want to say, hey, if a link is included in this list, for instance, for path 1, if a link is included in this list, then put theta LP equals to 1, and put it 0 if it is otherwise. For instance, if link 6 is included in path 3, then put theta 3, 6 equals to 1, and if it's not included, put it equals it to 0. That's what I want to do here. So I need 4 loops here. First one, 4 loops here. First loop over the paths, so P in P. And this P, capital P is basically the list or set of paths. And also I need another loop over lengths for L in L. And now I gotta define the criteria. So I say if L in path P, which means if this statement is true, because that's basically what in function does. So it says the output of in function is either true or false. So this one says if L is in path P, so it goes and check if each link is included in a path, in a certain path, then I gotta put theta, theta PL equals to 1. And also, if it is otherwise, else, I put theta P and L equals to 0. Let's see if I did it right. Yeah. So let's go over it again. What this line of codes do is it starts looping over P paths. So basically, it starts looping over this this P, and also then I start looping over L. Then it goes to this line, which is checking if L is included in path P. So the first loop over P is P equals to 1, right? So basically we get to this list. And in this list, what it does is first, because the first loop over L is 1, first this line of code checks if link 1 is included in path 1. And as it's included, we get to this line. It includes theta PL equals to 1. Basically, it's telling us that link L is included in path P. And if it's the other case, then the theta PL should be equals to 0. Okay, I think, oops, I'm sorry. This is 1, yeah. Now we're done with the parameter definition. Now we get to the next step, which is the model setup, or setting up the model. To set up the model, the very first things we gotta do is we gotta define the model. So I should define an abbreviation for the model. Let's use the MDL equals to, this is the keyword model. Then I gotta define a name for it. Let's say I can use example for learn force. Okay. That's how you define the model. Basically, you're telling the Python, I'm defining a model in Python. By the way, this model is the keyword in the library Gurobi Pi. And the abbreviation for that model is MDL, which means from now on, if I want to define anything related to this model, I got to use this MDL. This is the keyword for me. Okay. The next thing is defining variables. Oh, spelling is always my problem. Defining, yeah. Variables. I'm sorry. So how many variables do I got here? I have only one variable here, which is XA. That's a binary variable. And I can make it two variables, basically defining the objective function as another, this summation of XA equals to Z as another variable. But the art of programming and defining the problems in Gurobi and Python is to minimize the number of constraints that we need to have. So yeah, that's a possibility to define another variable like z equals to sigma xa, but it's better to avoid it because it increases the number of constraints we have. Okay, let's get back to our Jupyter. So we have variable x equals to, as I said, to say this x is going to be a variable pertaining to this model I define here, I got to use the MDL. So sorry, MDL. So the Python basically knows, hey, this is something related to this model, and the keyword is add vars. Here's the thing: this s is very important. If your variable doesn't have any subscript, you shouldn't use this s here. And if you do use the s, the Python will get back to you with an error saying, hey, this is only one variable, it doesn't have any subscript, why did you use s? But if your variable does have subscript, you got to use s. For instance, if I decided to go with defining another variable like z equals to sigma xa, because z wouldn't have any subscript, then if I had to define the z, I had to use just add var. But here, because x is a binary variable that includes subscript a or l in the model I defined at Jupyter, then I got to use the letter s. That's a tricky point you got to know. Okay, now we get to L for L in L. Wow, what does it mean? Basically, this list, the first thing I defined here is it's telling me what are the subscripts of this variable. Here I'm saying Python, hey, this x has the subscript L, and this L should be included in the set of capital L. And that's how it should be. And the next thing, I got to define the type of variable I have. And for that, I'm writing vtype equals to grb, which is e dot binary. And as you probably can guess from the name, grb.binary, it's telling Python this is a binary variable. I can also assign a name to it. I really want to do so. I define the name as x. So this is basically a string that's showing the name of the variable, just like how I defined the name of the model here. Okay, let's get to the next step, which is defining objective function. So using objective function. To define objective function, we have two steps. First of all, we gotta tell Python if you're doing minimization or maximization in this problem. For a problem, in this problem, you're doing the minimization, so we gotta let Python know that we want Python to minimize the problem. So again, I'm using the MDL to let Python know this belongs to the problem, and the keyword is model sense. And just be mindful, this S should be capital. Then I'm using equal and grb dot. Here I should tell Python either to do the maximization or minimization. We gotta do it with a capital letter and minimize. And the next thing is to define objective function itself. The objective function we had was a minimization, and it was over. Yeah, it was a minimization, and the summation was over the lengths, and we have this binary variable xa, which we define as xl in our model. So simply, I can write down again. I'm using MDL. Sorry, MDL dot. This keyword is set objective. Again, pay attention that this O should be capital letter, and open parenthesis, quick sum, And because we have a summation, quick sum, open parenthesis. And here we tell Python x, do it over xl. This is how we defined the subscript in Python. Let's say if the variable x had two subscript l and p, this is how I could have defined l and p as subscripts of x. But here, because x has only one subscript, we're using xl. Also, for the quick sum function, well, I gotta let Python know, okay, do the summation over what subscript. Here it's very easy because we have only L as subscript, but let's say if it was L and P, then I had to let Python where to do the summation, over what set it should do the summation. So here, again, I'm removing this P, and the way I can do it is like to say for L in the set capital letter L. And that's for the defining objective function. The next line, as you probably could have guessed, is a set of constraints. Yeah. So the constraints we have here, we have only one constraint, and that constraint is this line. So in this constraint, we do the summation again over the set of links, and it should be repeated for each path to assure that at least one link from each path is selected. Okay, so to do so, again, we use MDL dot. So to add constraint, we use add const rs. Again, this letter S is the tricky part here. If you have only one constraint and it shouldn't be repeated over anything or over any other parameter or set, I better to say set, then we got to use add constraint. Add constr. If you have a set of constraints that should be repeated over a parameter, over a set, sorry, then I gotta use the letter S here. To make it more sense, let me go back to the formulation we have here. Here we have sigma rho ARI times XA greater than 1, and we have a summation over A. But here it says for each Ri as a member of R, right? So we got a repeat constraint for each paths. So here we got to repeat the constraint over a set of paths. That means we got to use the letter S here. If this constraint was only for one path and we didn't have to repeat the constraint for other paths, I had to use the add const and remove this letter, this last letter. Okay, so I'm bringing it back as we do. We gotta repeat the constraint over the set of path. Again, we do the quick sum, open parenthesis, it was XL. And here in this example, I used the parameter theta. So I'm just saying copy and times paste, right? Okay. And here I gotta tell Python, okay, do the summation over what? You gotta do the summation over the set of links. So just like the previous line, I say for L and L. Here, and because it should be greater than 1, I say greater than equal 1. Now I gotta tell, Python that it should repeat the constant over the set of paths. So to do so, I simply can write for P in P. And that's how the Python do repeat the constraint over the set of path. Okay, so we are done with the constraints. We're done with the objective function and defining variables. Pretty much we're done with the model setup. And the next thing I gotta do, I gotta tell Python, hey, update the model, because It initially defined the model here. Now we get here, I got to tell Python, hey, I have some new lines of code. You got to add it to it. So to update the model, I'm writing mdl dot update. So basically update the model. Then the next line is to ask Python to optimize the model. And, the way we can write it is using, again, mdl dot optimize. The next line that we got to define is using status, basically asking Python to tell me the status of the model. The status might be infeasible, it might be optimal. So, and the keyword, again, I'm using MDL. The keyword for that is status. Basically, the Python, whatever is the status of the model, it puts it in the variable status. The next thing I want to say is not mandatory for solving the problem, but I found it as a very useful tool, especially in the case that you face an infeasible problem and you want to see how is the mathematical representation of the problem you implemented in Python. Then you can use this line of code. As I said, it's very useful to have a better understanding of what you did here and to find out any potential error that you might have in your code. To visually see the mathematical representation, what we can do, I can again use mdl dot, then I got to use the keyword write, open parenthesis. I'm just using example, example learn force. And also I got to put dot here, LP. Also, there's another version that it could be .rlp, but I found LP more useful as it's more user-friendly. It's a better mathematical representation, better to say. Also, what I can do, again, this is not mandatory for getting the results, but I like doing it in my codes. So I'm asking Python if the status equals to grb dot. In this line, I'm going to ask Python, capital, if the result the Python returns to me is optimal result, then I'm asking Python to basically print it for me. So status grb dot status dot optimal, which is one of the possible scenarios of the model result, optimal. Then I'm simply using print function and f-string formatting. So the optimal result is mdl dot obj val. Technically, I'm asking Python to print, if I'm getting the optimal value, to print this line, and also this mdl dot obj val, which is the abbreviated version of objective value, returns the objective value. So yeah, we are done with our model. I can simply press this line, this button to run the model. Let's see what happens. Okay, here we have an error. Oh, I forgot the last quotation. Oops. Let's do it again. Yep. Yeah, start running, and we get to the optimal value because we also the Python prints this line for me. So the optimal result is 1. You may also ask, okay, how we can get the values of decision variable In this problem, the decision variable was this x, which was a binary variable, right? To get the values of decision variable, it's also easy. It needs like 2 lines of code, basically. I can say, sorry, decision var. You can use whatever name you want here. This is just my favorite. Now the keyword is, again, I'm using MDL to let Python know I want something from the model. And then this is the keyword, and get which is, sorry, a short version for attributes. ATTR, open parenthesis, X. And here, you got to put the decision variable you want to have the values of that. Let's say if we had 2 decision variables, one of them was X, one of them was Y, and I want the values of Y here, I put Y here. This X inside the quotation, it's always fixed, but this one represents what variable that you want to see its values. Okay, and I'm asking Python just to basically print this. Yeah. So if I run this line of code, oh, sorry, we don't have Y, X. Yeah, so you can see from the 8 links we have, to minimize the number of links in each path, the number of links selected from each path, we only need to select link number 1. Also, I forgot to mention here, let's see, what did I mean by having the mathematical representation of the problem. So if I go here, I should have an LP. Yeah. So you can see this .lp file gives me the mathematical representation. It's basically the minimization over the number of links, and also it shows me the constraints here. And also it tells me these variables are binary. Okay, that was it for today. I hope you find this tutorial useful. And in the following tutorials, I'm going to talk more about how we can implement more complex problems in Python using Gurobi. Have a good day. Bye.